Testing, testing, testing. Jim Cecil, Brandon Steele. They aren't listening. Jim Cecil. Does that sound okay? Good? All right, we're going to try that. Okay, good, good. Just so I understand. So there's Good lunch. People are still coming in, but we're gonna go and get started because we have to finish on time so we can start everything else that's happened this afternoon. So I'm not gonna try to pronounce any names here, but this is an end-to-end flight software development cycle presentation. Right? That's yours? Hardwired microphone,
Oh, this one? Hi. Okay, thanks. So, good afternoon, everyone. My name is Mar, and today I'm going to present the end-to-end flight software development cycle for an interplanetary spacecraft mission in which LASP and the AVS laboratory at CU Boulder are collaborating. And we're going to see the complete flight software development cycle for this mission. So we'll start with the desktop algorithm design using the Basilisk software testbed. We'll then see migration from the Basilisk desktop environment into the core flight system middleware. And then we'll see embedded testing of the CFS flight software application in an emulated flat sat. And a couple of interesting aspects about this cycle are the transparent migration from desktop into CFS and consistent testing throughout testbeds by means of a distributed communication architecture. So this slide shows the development cycle illustrated graphically. And we're going to start with the Basilisk framework, where we prototype the flight software algorithms. We then migrate these algorithms into the core flight system in a transparent manner, and transparent meaning that the source code does not change for migration. And then we are ready to embed the CFS flight software application into a single board computer emulator in order to perform distributed closed-loop testing. And I would like to start with an overview of Basilisk, which is an open source cross-platform desktop testbed for designing flight algorithms and testing them in closed-loop dynamic simulation. So Basilisk leverages the use of Python for flight software development, provided the flight algorithm source code and the spacecraft simulation code are written exclusively in C and C++, and then simply wrapped into Python for setup, desktop execution, and post-processing. And this image over here shows the nominal configuration of a Basilisk simulation. There's a dynamic process containing spacecraft physical models written in C++, and a flight software process containing the mission-specific GNC algorithms written in C. And Basilisk is architected in a modular fashion, and during a simulation run, all these C and C++ models interact with each other through a message passing interface, or MPI. And the beauty of this MPI is that it marks a clear separation between the two processes. And this separation, later on, facilitates the migration of the flight application into a different processor. So Basilisk developed flight algorithms have imported to both commercial processors, like the Raspberry Pi, but also to a couple of different middleware layers, like the core flight system and, more recently, MicroPython. Although today I'm going to focus on CFS specifically. So what I'm going to describe next is what does it take to migrate the flight software algorithms from the Basilisk desktop environment, which is a combination between Python and C, into a pure C flight software application that can be readily integrated into CFS. So if you recall, Basilisk leveraged the use of Python for flight software setup, desktop execution, and post-processing. And there is one of these functionalities that needs to be translated from Python into C in order to come up with a complete pure C application. And this is the setup. And in the Basilisk framework, the setup code encompasses module variable initialization and task definition. And now we're going to see each of these two items one by one. So we'll start with the C module initialization. A Basilisk C module can be seen as a standalone model or piece of self-contained logic. So in the context of flight software, this could be a specific navigation filter, a very specific control flow. And here I'm showing an example of a very simple model, the vehicle configuration one, which simply contains vehicle static data that in a simulation run will be used by other models. All Basilisk models are characterized by having a configuration struct and 4 generic algorithm calls: self-init, cross-init, update, and reset, that are called from Python during desktop execution. So all these C models are wrapped in Swig and made available at the Python layer for initialization. And here we see the Python instantiation of the vehicle configuration model, as well as the initialization of its variables: inertia, center of mass, output message name. The second item that we handle through Python is the definition of tasks that run at certain rates. And any number of models can be added to each task. So here, there is an example of a Python instantiation of a flight software process, the creation of an initialization task, and the addition of the vehicle configuration data model into these tasks. So we have just seen which is this setup code that needs to be translated from Python into C. And a key remark here is that only the setup code needs to be translated for migration, and the flight algorithm source code remains unchanged. So the pure C flight software application is conformed by the modified flight algorithms plus one header and one source file containing this setup code. And the interesting part of the story is that the translation from Python into C is handled automatically via a third-party script, the autosetter.py, that we've developed for this purpose. And the beauty of the autosetter.py is that it's not a black box. It's different from autocoding in the sense that it's a very simple and transparent template that simply maps Python variable types into their C counterpart. And the resulting C setup code, it's minimal and looks like optimized human-written code. And the trick behind the autosetter.py is that Python is great at introspection. So Python is great at looking at itself, and introspection is something that cannot be achieved just with C and C++ without a significant effort in source parsing. So here I'm showing code snippets of the Python input to the autosetter.py and the C output. And because Python is great at introspection, the autosetter quickly realizes that in a given Python scenario script, there is a flight software process with this vehicle configuration model, and that some of its variables are actually initialized with non-zero values. So if we take a look at the inertia, for instance, in Python, this is initialized as a list of 9 floats, and the autosetter knows that in C, this unambiguously translates into an array of 9 doubles with only certain indices initialized. And this is a very simple example, but as long as you handle recursion and nested structures properly, in the end, the C variable types, they always boil down to the same ones. So the beauty of the autosetter is that it's very simple, but it's very powerful because it enables rapid iteration of the flight configuration back and forth desktop and embedded environments. So it's really a time saver. And now we've just seen, which is this, now we have seen that this setup code plus the modified flight algorithms conform a pure C flight software application, which we can then integrate into CFS and perform embedded testing. And in particular, I'm going to talk about embedded testing of the CFS flight software application in an emulated FlatSat. So in such configuration, CFS flight software runs within an SVC emulator and interacts with external world models for closed loop testing. However, once flight software is integrated into CFS and embedded into the SVC, it's no longer as simple to access the flight software states for reading and writing. And for this reason, it has been necessary to emulate the FPGA registers within the SVC emulator as well. And before describing further this FPGA register space, I would like to step back and talk about the specific FlatSat models that we use and the distributed communication architecture that supports this emulated FlatSat. So the for this spacecraft mission, the general concept of an emulated FlatSat has materialized in the configuration that is shown here. So the flight processor emulator we use is the open source QEMU, and we're emulating a Leon 3 board with RTMs running on top. Inside QEMU, there's also the CFS flight software executable, as well as the modeled FPGA registers. The spacecraft physical simulation we use is Basilisk, which handles dynamics, kinematics, and environment, but also models sensors, actuators, and complex avionics hardware. The ground system emulator we use is a LASP in-house model named Hydra, which contains the command and telemetry databases for this mission. And the visualization is an open source GUI that is available together with Basilisk. So the challenge of enabling communication between all these models is that all these applications all these are standalone applications that were never designed to work together. So they are completely heterogeneous. They are written in different programming languages, C++, C, Python, C#. They have different execution speeds. So some of them are asynchronous, like the ground system, which is event-driven, while others are synchronous, like CFS flight software or the spacecraft physical simulation. But even among the synchronous ones, they have different execution speeds. So QEMU, for instance, runs slower than real-time, but Basilisk runs natively way faster than real-time. In addition, some of them are multi-threaded, while others are single-threaded, which is something important when you think about communication and socket connections. They also have different NDNS, which is especially tricky to handle. So the integration of independent spacecraft mission models into a single simulation run demands for a solid communication architecture underneath. And on these lines, I'm going to briefly talk about Black Lion, a purely software-based communication architecture that we have developed in support to this mission. So Black Lion aims to achieve 4 communication goals. The first is the transport of binary data between nodes or applications. The second is serialization of binary data. So each application needs to know how to translate the received bytes into structured data that it can then handle internally. The third goal is synchronization. So all these components need to be kept in lockstep during a simulation run. And the fourth goal is to have dynamicity in this connection map. This means that none of these applications should be required. All of them should be like clients that can come and go without bringing down the entire system. So Black Lion aims to achieve these 4 communication goals while remaining as abstracted as possible from the internals of each node. So this means that we don't really want to heavily modify the source code of each application. And with this purpose in mind, Black Lion has been designed with a unique central controller and 2 APIs, the delegate and the router. Both of them are attached to each of the nodes. So the central controller acts as a message broker and a master for synchronization. The delegate API manages sockets and direct connections with the central controller, and the router functionality is to route internal data in and out from the node's internal. So Black Lion uses a tick-tock mechanism in order to maintain all the nodes in lockstep and achieve synchronization. So the central controller sends a tick command to all the applications, and then each of them publishes its own internal data. It subscribes to fresh data from the external wall, and if the application is synchronous, it steps forward for the commanded time step. At the end of this, each application talks and sits there waiting for the central controller to send the next tick, which won't happen until all the applications have talked. So this is how we achieve the lockstep. Okay, so this has been an overview of the Black Lion communication architecture, and from now onwards, I'm going to represent this distributed communication with this simple TCP sign. And what I would like to focus on is on the FPGA registers that we have modeled within the SBC emulator, because all the flight software states that need to be shared with the external world, they are mapped into these registers. And we have modeled a total of 4 register boards, and each register has a memory buffer associated, so the shared flight software states are mapped to this buffer. And I'm going to refer to these shared flight software states as snorkels, in the sense that they are direct connection pipes to the internals of the CFS flight software application. So through these registers, flight software reads and writes in a hardware-like fashion that also replicates board interrupts. And together with the register modeling, we have expanded the spacecraft physical simulation with complex avionics hardware, which leverage some functionality that would otherwise have to happen within the register space as well. So a couple of examples of these avionic hardware models are the PCU, responsible of managing controller, switch, and propulsion cards, or the IPC, responsible of retrieving and storing NVM commands and producing housekeeping packets. So within each register space, we have modeled a bunch of snorkels. There are snorkels related to actuators, like reaction wheel commands from flight software, reaction wheel speeds to flight software. There are snorkels related to sensors, like the Corsan sensor or the star tracker. We have snorkels related to the avionics model, PCU, IPC. We also have snorkels related to time. There are a couple of clocks, the master VTC clock and the slave VTC clock. And we also have snorkels for command and for telemetry. And the trickiest part of all these snorkels is that each of them is pretty unique. So they share some basic features, but their internal operations are completely different. So some of these snorkels are unidirectional, either readers or writers with respect to flight software, while others are bidirectional. Some of them operate only on a packet address, while others also need an address, a descriptor address, where the descriptor is describing something important about the packet. Some snorkels store single word packets, while others need to queue them up. Some of these packets have fixed size, while most of them are variable sized. The snorkels related to command and telemetry need to also add or remove byte headers to the packet depending on the, depending on the direction. And most of them need to handle NDNS because QEMU is little endian. So now I'm going to show a couple of numerical simulations which showcase the use of these registers. So the first simulation will encompass several spacecraft pointing maneuvers that are manually triggered by the user using the command database interface. So we'll see how the user enables flight software monitoring, commands the spacecraft to inertial pointing, correlates the ephemeris, commands Mars pointing, switch to SAM pointing, and back to Mars pointing. And the second numerical simulation will be a video of Mars orbit insertion. And a few interesting things that we'll see is a time jump. So we'll put the spacecraft into a sort of wormhole and bring it right before MOI. We'll also see the delta V burns, of course, which are related to the propulsion cars within the PCU. And most interestingly, we'll see a lot of nominal testing, where there will be several modeled flight software resets and of nominal star tracker acquisition. But before that, we'll start with a spacecraft pointing maneuvers. So these plots show the evolution of the spacecraft, principal attitude in a simulated closed loop, as seen by the spacecraft physical simulation. So the spacecraft initially starts at a certain attitude with flight software not yet doing anything, and then the user enables flight software monitoring, and it commands the spacecraft into several pointing modes. And during this closed loop run, again, all the flight software states like sensor data, command, telemetry, reaction wheel torques, they are all stored in these registers. It's not working. I'm not sure if there is another slide or not, but we can switch to the video, that's fine. So the video is the second, yeah, there we go. So the video is the second numerical simulation I'm going to show using the visualization in a closed loop. And here we start pretty far away from Mars, and we see the time jump. We bring the space. Let's see. Okay, there we go. So we bring the spacecraft right before MOI, and we're trying to stabilize its attitude in order to start the burn. So this should happen soon. There we go. Now we will start the delta V burn. but there will be a flight software reset. And we come back again. And the spacecraft will try to stabilize its attitude again, but the start trackers are not reconfigured properly. So we'll see the spacecraft has a hard time resuming the delta V burn. There will be more flight software resets. So as I mentioned, this is a pretty of nominal testing. But we'll make it there. And there we go. We start the DV burn again. Yet there will be yet another reset. But we resume, and now if we scroll, if we zoom out, we'll see that the hyperbolic orbit, if you can see that, will become elliptical, and the orbit will start shrinking down, and yeah, we're finally captured, and that's the end of the burn. So yeah, that's all I have. And if you have any questions, I'll be very happy to take them. Thank you for your attention.
Thank you. Glasses, someone lost glasses. Someone handed them to me earlier. They're Foster Grants. If you lost some, come see me. I'll get them to you. By the way, it's snowing outside. So we went from 50 plus degrees yesterday to snow right now. So less than 24 hours. So welcome to Alabama. So we're going to not postpone. We're going to not have any time for questions. Okay. So our next speakers are from TT Tech. So TT Tech is one of our sponsors. And it looks like the wired mic up here is working just fine. So hopefully you'll be fine.
All right, good afternoon, everyone. I'm Bob Richards. I'm from the U.S. office of TT Tech, and myself and Matt Sweeney are going to be giving you an overview of how the TTE tools and products are going to be used to support the gateway. So TT Tech supports many different industries: automotive, factory automation, civil aviation including flight controls and fault-tolerant subsystems, et cetera. But my emphasis is on the space. I lead the space activities in the U.S. here, and you know, human space flight, as we've talked about in this conference, the Artemis program, the Gateway, is really a national priority, and NASA has set open standards for the Gateway, and those open standards include time-triggered Ethernet and other things which TT Tech will definitely be supporting. So if you, let's see, I guess I've got the clicker. So today we're going to just give you a quick overview of you know, what the Gateway is shaping up with for data backbone products, and then how some of the TT Tech products can be used to support the time-triggered Ethernet data backbone at Gateway, and also a little bit about our development environments and how we think that application software could be developed on these development systems to be most efficient and take advantage of the capabilities of the TT Tech products. So Gateway is still in formulation, but you know, one thing's for sure, it's a 3-lane data backbone, and it's a switch-based system using time-triggered Ethernet. The exact number of switches, the exact number of end systems is still in, you know, design, and we're supporting the various prime contractors and NASA for that determination. But sort of schematically, you can see that different modules are designed to connect together. And the gateway also, it's basically the entire Artemis program. So the gateway includes anything that touches the gateway, like a lunar lander, or like the Orion vehicle itself, or a deep space cargo vehicle that's delivering supplies to the gateway. And the gateway has to also operate in different configurations, much like the International Space Station where it starts out. It's a single module, and then over time it grows. So having a data bus configuration that can grow over time is also very important. So this is a sort of notional set of avionics. This is actually a NASA slide. Give you a sense of the types of functionality that Gateway is going to have to operate with. And you can also see that different types of traffic types are also defined on this chart with best effort, rate constrained, and time triggered. And Matt's going to kind of go through a little bit more details on what all that means. But this kind of gives you a sense of the types of functionality that has to be accommodated on the Gateway, and also that the sort of center of it is one fault-tolerant command and data handling system, of which the TTE products can support as well. So the NASA open standards could be kind of capsulized as it relates to the data bus and software into these elements: a time-triggered Ethernet data backbone. NASA specifies, or maybe specifies a little too strong, but basically likes the DIMA type of approach, distributed integrated modular avionics, which uses time-space partitioning, such as ARINC 653, to allow different functions, which can even have different levels of criticality, safety criticality, to operate on the same processor. And then also they support the CFS software infrastructure for the basic type of infrastructure for software. And the advantages of this is lower mass for cable harness. With a switch-based system and high data rates, you're really going to cut down on the point-to-point wiring and the overall cable harness mass. In fact, this is an older system, but it's public knowledge that the International Space Station has more than 120 mil-standard 1553 buses. So if you don't use a technology like this, you can end up having to have lanes of criticality on top of additional lanes for redundancy. And it really adds up on the number of data buses and the cable harness mass. And then by having time-space partitioning such that you can put different functionalities on fewer numbers of computers, you save mass and performance there. Also, this gateway system is unmanned for 11 months out of the year, so automation is a really big deal, and maintainability is a really big deal, because it's probably going to have a lifetime of 15 years or more. So we as a company support NASA's vision for the Gateway with these types of features. I'd say the only sort of trade-off for getting these advantages using time-triggered Ethernet is you do have to schedule the network. It's an extra piece of work. You put a little bit more work in up front, and it pays dividends in the fault tolerance aspects and the operation of the network itself. So, Matt, over to you.
All right, thanks, Bob. So Bob talked about TT Ethernet and some of the advantages of using it, but over the next few slides I'll talk about how it works and what the principles are behind it. So TT Ethernet allows for the use of 3 different traffic classes. There's the basic IEEE 802.3 Ethernet, also referred to as best effort Ethernet. This comes with no performance guarantees at all. But then a step above that is ARINC 664 Part 7, which is rate constrained. Basically, the amount of data that is sent out in a given length of time is restricted. So this is still asynchronous, just like best effort Ethernet, but it does give you a lower jitter and a latency of somewhere between 1 and 10 milliseconds. But then another step above that is the SAE 6802 time-triggered Ethernet, which is the big advantage of TT Ethernet. This is synchronous deterministic Ethernet. Like Bob said, it's scheduled ahead of time, so it's all completely planned out from the start. This allows for very low jitter, below 1 millisecond, and it's a known latency because you know when data is going to be sent and when data is going to be received as well. So on the bottom of this slide, you can see 4 different base periods of, this is the schedule of an end system sending different frames of data throughout the network, and the gray time-triggered boxes are scheduled ahead of time. And what happens with the best effort and rate-constrained data is those are used to fill in the gaps whenever scheduled data isn't being sent. So one way I find helpful to explain the concept of time-triggered Ethernet is comparing time-triggered and event-triggered and an analogy of transportation instead of data on a network. So we all know cars and taxis, and they're event-triggered because they travel whenever they're needed. You can just hop in a car and decide to go, and it goes then. So the advantage there is it's flexible. But the disadvantage of using a car is what you can see on the right. You might run into a traffic jam because maybe everyone wants to use the network at the same time, or the road. So this is where time-triggered comes in. They are not event-triggered, it's time-triggered. So trains and subways operate according to a fixed schedule. They all agree on what the current time is, and they all have their own agreed upon schedule. And due to this, it's very predictable. When you hop on a train, you know when you're going to leave one station and when you're going to arrive in another one, or at least it's supposed to be predictable. So deterministic Ethernet is this time-triggered example, more like trains and subways than cars and taxis. So now you can see this is an example of a piece of time-triggered data flowing through a network from the end system on the left to the 2 end systems on the right. You can see 4 of these nodes. You have an end system, then 2 switches, and then 2 end systems on the side. And 4 of them are time-triggered. These are the blue ones with a clock, and 1 is not time-triggered. And each time-triggered node has its own version of a schedule. So on the left, it wants to transmit M at 10:45. So all it needs to do is transmit M at 10:45. And the first switch it runs into says, I will only accept M between 10:40 and 10:50 because it's scheduled to receive it sometime immediately after it's transmitted from the first end system. So it has a receive window and not an exact time, but it's still highly scheduled. And the schedule carries forward, going from that switch to the next switch and the next switch to the time-triggered end system. There's always a plan for what time it's going to be transferred and what time it's going to be received by a switch or an end system. And we also have the non-time triggered end system in this example. It can be a part of the network, but it's not, it doesn't take part in time triggered communication. So it just receives that frame M whenever it comes. It doesn't have a receive window. All right. So I talked about the need to plan the network ahead of time. You need to figure out basically the network setup and what kind of traffic you want on it. So TT Tech provides a suite of TT Ethernet development tools. These are essential software tools for the design and configuration of TT Ethernet and AFTX networks. So when you plan your network, you're going to use TTE plan, and you can put in switches and systems, different cables, redundancies. You can specify what kind of traffic, whether time triggered, best effort, or rate constrained is going to be on the network. And then using TTE plan, you get a network configuration out of that. And then TTE build separates that out into device configurations. And device configurations are loaded onto your network, the switches and the end systems, using the TFTP loader there. And you can see we also have tools like TTE verify and TTE analyze. These are independent verification tools, and you can perform network analysis just to ensure the network is behaving as you specified at the start. Okay, so once you've planned the network and you've created those device configurations, what are you going to be loading them onto? So these are the TTE controllers for space. You can see on the left, there's the TTE end system controller, and on the right is the TTE switch controller. And they look exactly the same because the hardware is the same. The only difference is the firmware loaded onto them. But there are two different versions. There's the space grade ceramic package and the high-rel plastic package. TT Tech recommends use of high-rel plastic for early development and testing, and then moving on to the space grade ceramic package for advanced testing and in-flight use. Okay, moving up from the controller to the card level, this is the TT Ethernet platform for outer space. On the left and in the middle, there's the TT Switch Space CPCI card and the End System Space CPCI card. The Switch contains 12 Ethernet ports, 6 gig speed, 600 megabit speed, and the End System contains 3 gig speed. They're all IASIS compliant, and you can see the low weights there of 600 grams for the Switch, 400 grams for the End System, and they use low power as well. And then on the right is the avionics hosting unit, where the cards can slot in. There's 4 CPCI card slots, as well as a processor, where TT Tech recommends the use of AI Tech, what was it called? Yeah, AI Tech SP0 for the processor, but really whichever one meets your needs, you can use. And that one also comes with a low weight and provides power for the cards. And moving on to the development level, Bob will take back over.
Yeah, so I'll kind of finish up, but you can see we're developing a whole suite of not only space hardware, things that could be on the gateway or could be inside a lunar lander or whatever, but I want to spend a little bit of time on the development tools as well. And of course, really the prime contractors for those systems are going to make the sort of final decision on what tools and what processors and what configuration ends up. But we want to emphasize that based on experience that comes through from the airplane industry and other things, we can, I think, help the primes have the most smooth approach to software development. So here's an example of a development system that we've had around for quite a while, and these are shipping all the time, that has multiple switches and multiple end systems, and it has essentially the ASIC, the plastic ASIC, inside these PCs for tying into the time-triggered Ethernet network. And this operates with Linux as the operating system, and this is what we would suggest that you start with. And more specifically, for Gateway, we would want to introduce CFS into the mix as well. So you'd start with this development system that I showed in the previous chart, and you would have CFS sitting on top of Linux, and then that is talking to an end system, and then that ties into the switch, and you'll have a sort of mini network right there operating. You use this environment to start with because it's the lowest cost. It's sort of the easiest to deal with Linux. A large number of software engineers understand Linux very well. They're easier to find and stuff. And you would develop your apps for CFS in this environment. You can also exercise basic sending data to the network and getting data back, get all that up and running. And if timing is important to you, there's also some middleware that we can provide that ties the CFS scheduler to the time-triggered Ethernet clock. Because again, we didn't really harp on it too much, but the other big piece of this whole network is there's network time that's distributed to all the nodes, and there's a methodology when you bring two networks together to decide, do they stay separate and from a timing point of view, or is one considered a higher priority than another, and so the lower priority will synchronize to the higher priority. So in this environment, you can be tied to time-triggered Ethernet time and be running on your CFS app, get started. But for the actual flight system, we think it's important to move into a more robust RTOS situation. So again, we're recommending a time-space partitioned operating system that CFS would sit on top of or inside of partition. And our company's got the most experience with ARINC 653 because that's a standard for the airline or airframe, civil airframe industry, and there's a lot of certification work already done on that. You could also use other time-space partitioned operating systems. It would work just as well. So moving from that other setup to a setup that has like a VxWorks 653 or something like that, then you can get into actual hardware in the loop types of simulations, a verification process, and ready for flight aspect. Also, for Gateway in particular, there's a whole nother additional verification that goes on the tail end of that, which involves NASA hardware. And without spending a lot of time on it, NASA's building a complete verification facility for the Gateway, similar to what they have today with ISS, where if you have a new flight system, you can plug your flight system into the ISS simulator and make sure it all works. The same thing will happen with Gateway, where you'll be able to plug your, let's say, lunar lander simulation or actual real flight hardware into the Gateway simulator and go through final verification process that way. So this two-step process has been tried out on real flight programs under the Next Step program that NASA has funded. It worked really well. And even you can have multiple contractors that come together and each person puts their CFS version into a different partition. Worked really well. And the time-triggered Ethernet drivers for using 653 tie a partition timing to the network timing. So in a multi-processor environment, each one is running their own operating system, but their partitions where their fundamental software is running are tied to the network time and therefore can be compared to each other for fault tolerance reasons. And it all works out great. So anyway, that's kind of a real top-level view of how we would recommend that you would do a software development for Gateway. It's a cool thing. It's a national priority, and we're very proud to be part of it and hopefully provide some good solutions for NASA and the nation. Any questions?
One back here.
So I get that TTE is all about time sync and all that fun stuff. Do you provide ability to sync from an external source, say like GPS or some other source?
There's definitely ways of doing that. So we've looked at syncing the network to an absolute time, I think is what you're saying. As far as Gateway itself, that's part of the discussion that's going on because there is no GPS in cislunar, and as long as the Gateway stays self-consistent within the Gateway, that's probably the most important thing, as opposed to being synchronized to an absolute source. But anyway, the answer is yes, and it's an architectural question that's still being discussed.
Okay. Thanks.
So you had said that Gateway needs to be reconfigurable as modules are added, but also that for time-triggered Ethernet, you need to come up with a network schedule in advance, like pre-plan it. How are those two worlds going to work together?
So it's a very good question, and basically you pre-configure the fact that there's going to be modules that are going to come in, okay? And then when they attach, they know how to the attaching point, like the lunar lander, knows how to join the network. The other thing is, although this has to be a pre-planned network, from a maintenance point of view, this network schedule is going to be changed, kind of over and over, but not on like a day-by-day basis, but more like maybe reconfigured just before a new module shows up and stuff like that. And there is a methodology for the switch to carry multiple schedules, so you can kind of load one while you're still operating on a good one, and there's actually 3 schedules that each switch can carry, and a methodology to switch between them. So your concern has been handled by the network, and it definitely will work.
We can answer one more question.
You mentioned support for VxWorks. Do you also support RTIMs or other RTOSs?
Not so far, but we're sort of a merchant supplier, so there's definitely discussion on different operating systems, and the Europeans are going to be getting into this as well. They have a European module called the IHAB, and I know there's a lot of discussion on what operating system they want to use, and so just come and talk to us. I'd say in general, sort of the final thing, get off the stage here, is we have several of our engineers and management from Vienna, Austria, the home office. We have our local U.S. people as well. We're going to be here for another couple of days. Please stop by, find us, and be happy to talk about any of these little issues. And we're also interested in things just like what you brought up. Well, this type of operating system or this type of middleware is really important to me. How do I get a driver for it, or something like that?
Great, thank you.
All right, thank you.
Thank you very much.
All right.
Thanks.
Hello, everyone. My name is Adil Rizvi, and I'm here with my teammate Kevin Ortega. We work on 2 separate CubeSat missions, Lunar Flashlight and Near-Earth Asteroid Scout, short form NEASCOUT. And we're going to be talking about the F-Prime flight software framework and our application of that framework for the 2 separate CubeSat missions. Now, we were planned to present this presentation yesterday, so that's why it's 12:09, but we got swapped to today. So, first of all, I want to talk about what is F-Prime. F-Prime, it's an open source software framework that facilitates development of embedded applications, in particular flight software applications. Now, F-Prime provides an architectural method to decompose your software system into components, and these components have ports which are type specific, and you're able to connect the ports into a topology. So that's at the core of F-Prime. And in addition to that, it's a C++ framework which provides for you, several features such as threading, OS abstraction layers, and message passing. And it comes with a suite of auto-coding tools that allow you to translate your code from a formal specification into base classes, which is basically, some boilerplate code that you're able to go off and do your hand-coded development from. And there's also tools to auto-code your topology as well. Also, F-Prime has a growing set of components that are included in its library. Now, some of the basic components include things like command dispatching, telemetry, and all the basic flight software services. And the set of these library components just keeps growing over time. That can be reused and inherited by other missions. Also, we have a suite of testing tools, including unit testing, integration testing tools, and Kevin will actually go into a little bit more on random scenario-based testing that we've been doing with F-Prime as well. All right, so let's talk a little bit about where F-Prime has been used so far. So F Prime first started out at JPL as a research development task back in 2013, and an initial version of that flew on the RapidScat mission, which went to the ISS. And next, it was also deployed on Asteria, which launched, it was deployed in 2017. Also, it's being used on the Mars Helicopter project, and you'll hear more from Tim Canham on that later on Thursday. Now, Kevin and I will be talking about Lunar Flashlight and NeoScout, our application of F Prime on those two CubeSats, and also it's used on several autonomy research and development tasks on lab. So just a little bit more about Lunar Flashlight and NeoScout CubeSats. So Lunar Flashlight, it's a mission to go to the moon. We're going to orbit the moon. We're going to fly by the southern pole very close. And as we're flying by the southern pole, we're going to be collecting data from the southern pole using the laser and spectrometer system on board to help us better understand the makeup of the southern pole, understand if there is water content on the southern pole. Eventually, we want to create an ice map that can help us better understand if humans can be sent there for further exploration. NeoScout, it's a mission to go to a near-Earth asteroid. We'll have a camera on board that we're going to use to take images of the asteroid as we fly by it very close. And those images will help us better understand the makeup of these asteroids before we can send humans to a destination like that. They're both 6-year CubeSat missions. One is going to the moon, the other one is going to a near-Earth asteroid. And they do have a lot of other similarities in common, which I'll get into in just a minute. But the thing I want to highlight here is these are two very different missions in terms of their capabilities and what they will be doing. But there's really only a single team to work on the two CubeSats. And you know, we've really had about 2 to 3 people for the majority of the development time for the two missions. And there's very aggressive schedule for the two CubeSats, as you can imagine, working on 2 separate missions, given the timeline that we have. And there's not a lot of margin for error and addressing bugs and issues as they come up, because you have to keep up with the project deadlines as it progresses in its own timeline. This kind of forces us to leverage a lot of existing software or whatever inheritance we can gain from existing missions, past missions. So that is something that we have really looked into. And also, having a mindset of working as a single team that's working to deploy 2 deployments, rather than having the mindset of having 2 separate teams working on 2 different missions. So having that mindset of having the same team, the core team, which is going to deploy 2 different deployments, that's really helped us deliver 2 separate mission flight software deployments concurrently, working in parallel. So I'm going to talk a little bit about the hardware configurations of the 2 missions. So they both use the same Sphinx CNDH board, so that's our compute platform. It uses a GR712 Spark Leon 3 based processor. And we have the same interface board on both missions, which routes all your data interfaces, and it has a couple of ADCs that we use to read data from. We have the same Iris radio, and we have the same power card. So this is what's all the common stuff in hardware across the 2 different missions. Now, Lunar Flashlight has its own specific guidance, navigation, and control hardware, and its own specific payload instrument. And similarly, NeoScout has its own set of GNC hardware, and NeoScout-specific solar sail and active mass translation unit, and its own specific science payload. So this diagram just kind of highlights the commonalities and the differences in the 2 different CubeSats. Now, how do we translate that into software for us to leverage the commonality from hardware into software? So what we've done is we've kind of tried to mimic that in software, and everything that you see up here, this is how we have characterized everything as being common between the 2 CubeSats. And that essentially lives in a separate repository, and it's the common shared code base between the 2 different missions. And we develop Lunar Flashlight specific components in a separate repository, and NeoScout specific components in a separate repository. And essentially, when we want to deploy for a Lunar Flashlight, we're built for the Lunar Flashlight deployment, building against the exact same code base. And when we want to deploy for NeoScout, we use the same code base, and we deploy for NeoScout. So as you can see, there's a lot of commonality between the 2 different deployments. And using the framework, we're able to leverage that and able to deploy 2 separate deployments with a lot of commonality between the two. So we're able to share the same code base across multiple deployments. We have a lunar flashlight deployment, NeoScout deployment. Also, software reusability and modularity at the component level. So with the framework, what we're able to do is we're able to drag and drop, in many instances, components that have been developed for other missions. For example, Asteria, and I want to give a shout out to Kevin Dinkel. He actually worked on Asteria, and we're using a couple of components from the Asteria mission for lunar flashlight and NeoScout as well. And there are several components that we have developed on lunar flashlight and NeoScout, which actually add to the F prime code base that can be used for future missions as well. For example, we have an entire Sphinx driver library that we've developed that can be used on other missions, and it could simply be a simple drag and drop as we used on the Asteria components. So with that, I'll have Kevin go over a little bit about on our software metrics here.
Hi, everyone. So a valid question you all may have is, how much of the code is actually shared between Lunar Flashlight and NeoScout? So if you're looking at the numbers here, we see that the number of lines of code in common is about 245,000 plus. Looking at Lunar Flashlight, it has about 69,000 plus, and that is on top of what's in common. So if we look at Lunar Flashlight in total, about 79% or 78% of its code is actually common, and 22% was actually specifically designed and developed for Lunar Flashlight itself. Looking at NeoScout, we have about 71% of its code base common, and 29% of it is actually developed for NeoScout. So in total, if we take the total amount of code developed for these 3 repositories, we have about 59% of identical shared code among the 2 missions. So it's similar. It's like we developed 2 missions in the time frame of a single mission. And mind you that the common code is in a single repository that is referenced by a Lunar Flashlight and NeoScout. So if there is a bug that was found in Lunar Flashlight and fixed, that bug fix would then propagate into the NeoScout mission. So F Prime has tools for rapid development. In the first stage of development, we do a modeling. So we use the system modeling language that's extended for F Prime. This enables formal modelization of the F Prime components, the ports, and the component topologies. So we use a Magic Draw and an in-house plugin to architecturally verify the F Prime software modules and to auto-generate the F Prime XML specifications. The second stage is translating this XML into actual flight code. So there's an autocoder that F Prime provides, and this autocode would translate the XML to the C++ F Prime base classes. It'll generate the commands and telemetry dictionaries that are products to the native F Prime GDS, or it can be provided to a GDS of your choice. For Lunar Flashlight NeoScout, we actually use AMPCS. And the autocoder also provided GDS for the initial tests, where we ran for the first time on the Sphinx platform. We were able to send commands and receive telemetry with the F Prime GDS. So a little bit more about the unit testing. So F Prime uses the Google Test Framework, and the autocoder generates this tester component that automatically connects itself with the component that you're testing, which in this case for this example, we'll call it flight software info. Then on top of that, you have this unit test that the user implements the unit test logic in this component. So in this part, the unit test can send a command to the component and verify command responses or telemetry or component state changes as expected. Next we have the rules-based testing. So here we have these rules that we define, and we'll define it for an example component called File Uplink Manager. So say you want to define these 2 rules. One rule is you have file uplink, you have uplink successful verify, And the second rule is uplink failure verify. And each rule will have a precondition. These precondition is essentially a Boolean function that indicates whether a rule can be applied or not. So for the unsuccessful verify, a precondition could be that the file doesn't already exist at the destination. And for the failure case, the precondition could be that the file already exists at the destination. And then you have your action. This is implemented by the user, and here you would just command the system and verify command responses and telemetry, similar to the unit test that you wrote here. So then we have our rules defined, and then we were able to create scenarios. So the scenarios is how we apply these rules in a particular order. But we actually use a random-based scenario testing. So we list out the rules, and then we go through n iterations. And then through those iterations, we just pick a rule at random. And then the thing about this is that once you apply the rule, the state changes of the component persist across the other rule applications. So you're really exercising your component in ways that it would take you a really long time to come up with that scenario. And all this is thrown into a continuous integration system that runs nightly. So it'll tell us whether the build failed or unit test failed, and it'll give us an email at night. So we do run on the flight hardware, the avionics testbed, or the ATB for short. And here you have the Sphinx platform. We have the Iris radio, some instruments, the RCS propulsion system, and the exact. And all this is connected to the ground system, which is just running AMPCS. And then we have this functional and integration testing scripts where we can automate the sending of commands and verification of the command responses and telemetry. And the neat thing about this is since more than half of our code is shared, we can reuse the script that's written for Lunar Flashlight with NeoScout. All right, so another thing is F Prime is open source. You can go to this link. It's on the NASA GitHub website. And here is a link to our F Prime small sat conference paper, if y'all are interested. And one thing that we want to highlight is that we were able to meet aggressive time schedules using F Prime. We were able to inherited components from previous projects. We were able to share a lot of the components between the missions, and we were able to.
The only thing I would add on to that is the last bullet there, the collaborative flight software development across multiple mission deployments, that being the crucial behind us delivering for 2 separate missions in the timeline of a single mission. It's this mindset and this approach towards developing our software, particularly using F Prime, which enabled it, is we're treating Lunar Flashlight and NeoScout as 2 separate deployments of a common shared code base, rather than developing 2 separate code bases. So with that, we're ready for some questions.
That's good.
Hi, this is Justin from the Aerospace Corporation. I had a chance to meet with Jeff Levinson just briefly about this. Excuse me. Question, is any of the F Prime code base legacy from any of the larger flight projects like Mars 2020 or MSL, or I didn't know how much of it is completely new versus just kind of a cherry picking of the best of the past?
Right, so that's a good question. So in terms of services, I would say, the amount of services we have in F Prime, or not just F Prime, but Lunar Flashlight, NeoScout, they're really not all that short from a large-scale mission such as MSL or Mars 2020 or any other flagship type mission. You have the same services of commanding, telemetry, timekeeping, memory management, scrubbing of the memory. All of that we still have to do for Lunar Flashlight NeoScout file system. The things that that's different for Lunar Flashlight NeoScout compared to a large-scale mission, it's really in the areas of having multiple payloads, having far more interfaces, or not having dual threads, having a single thread. So it's things like that. In terms of services, I don't think it's all that different. Now, of course, the components are written in C++ in F prime versus just a normal C for MSL or 2020. But a lot of the same services exist in F prime.
I have a quick question concerning the Sphinx CDH. Is that open source as well? And if so, where can I have a look at it?
That's a good question. So the philosophy behind it, I think, is kind of like having a Raspberry Pi for space. You know, being able to have a board that you can use for multiple different missions. It gives you many different peripherals. That is a JPL-specific developed hardware platform. I'm not sure if it's open source or not. It's something outside our section which is developed. So I can't completely answer to that question.
We have run F prime on Raspberry. We have run F prime on Raspberry Pis and other Linux workstations. So I don't know if that helps you in any way.
So just to clarify then, the CDH is more than just command and data handling as like a piece of software. It's actually like a piece of hardware that happens to do the CDH at the same time.
Oh, the CNDH is the hardware. It's the hardware computing platform. So that has your processor, it has your memory, it has your peripherals. That's not the software. The software is F prime.
Okay. So then does F prime do telemetry to the command?
Yes.
Parsing and emission? Okay.
Yes.
Okay.
Yeah.
Yeah, I've already started on GitHub. Thanks.
Yeah.
Other questions?
So your rules-based testing system, it seems like, I don't know what kind of order of rules you have, but there's like a kind of a combinatoric problem in just kind of putting rules together to get random results. Right. Do you know of any like coverage estimates of what the total number of like coverage of the rule combinations you get? And then how can you tell, is it like easy to tell when rules get combined if that's like actually corresponds to a scenario that you might encounter in the mission?
Yes. So that again is a good question. So see, with the rules-based testing, the key there is really understanding what is a good rule, right? And which rule is really going to test the code the way you intend it to be tested or for it to be used. I think in practice, rules-based testing really helps you with not just code coverage, but really branch coverage. It's able to, you're able to test out all the different branches and paths in your code by just defining different types of rules, preconditions, and actions that you want to test. And of course, with that, you definitely get a lot more code coverage that you would with just your normal hand-coded unit testing.
And F prime does have this this tool that allows to it'll tell you the code coverage percentage-wise of your code. So
right, so you can always run your analysis on what's the code coverage you're getting after you've ran your particular set of rules.
Anyone else? Okay, so we were going to have a Rust Splinter session. Is that room available? Okay, so this is, thank you, by the way.
oh yeah.
So this, so we're going to take a break. Before we do, I'm going to throw the other slides up real quick. We have another Splinter session this afternoon about Rust. It'll be over at the Teachers Lounge, which is basically, if you go through this wall right here, the door is like right there, and it says Teachers Lounge on a sign out there. That'll be from like 2:30 to 3:30. Of course, we have everything else going on. If you're going to the Marshall tour, number one, you have to be a U.S. citizen, right? So make sure you bring your badge. It has a green sticker on it, or you bring a piece of identification. And remember, we're going to be meeting, you might want to carpool. We're going to be meeting at the Rocket City Tavern, which is, we said before, was Gate 9, or the Redstone Visitor Center. The location on the online that we have for the Redstone Arsenal Gate Visitor Center is basically, it's the same place, except you're going to drive a little bit further down to the Rocket City Tavern, and you're going to park near the road. So it's like another couple hundred yards is where we're going to meet near in the parking lot. There'll be like 5 vans in there. So if you miss us, anyway, if you get to the gate, turn around. You went too far. We're going to leave like at 2:40, so it takes at least 10 minutes to get there. Don't cut your time short because they want to leave at 2:40 and be on our way. Anyway, thank you. Oh, one question? So we've you've already signed up for it?
Yeah, I've already signed up and paid for it.
though, if you go to that locations link, and I don't think we have it up here, go to the website. The Surveyor's one of the restaurants.